In this video, we are going to learn about orbitals and electron configurations. In the last video, we learned that orbitals are regions of high probability of finding an electron, and we also learned how to read the periodic table to determine the general energy order in which orbitals fill. Now we are going to demonstrate how electrons fill these orbitals by creating an orbital box diagram. Generally speaking, electrons try to minimize their energy. The lowest energy arrangement of electrons is called the ground state. There are three principles that guide how electrons fill these orbitals. The first is called the off-bow principle, which states that orbitals fill from the lowest energy to the highest energy. The second rule applies when there are multiple orbitals of the same energy. In that case, electrons will occupy each orbital one at a time before pairing up. This is known as Hund's rule. You can think of Hund's rule like seats on a bus. If there are lots of empty rows, you usually do not sit next to a stranger. Only after all the rows have one person does it become socially acceptable to sit next to someone else. The final principle is that each orbital can hold a maximum of 2 electrons. When 2 electrons occupy the same orbital, they must have opposite spins. One spin up and one spin down. This is known as the Pauli exclusion principle. Now we are ready to draw an orbital box diagram. At the bottom of the diagram, we place the lowest energy subshell, which is the 1s. The number represents the shell, and the letter represents the subshell. Next to the 1s, we label and draw one line to represent single orbital in the s subshell. You can draw full boxes. Moving upward in energy, we list the additional subshells such as 2s, 2p, 3s, 3p, and 4s. Again, you may see these drawn as boxes, but I am going to be using lines. Arrows are going to be used to represent the electrons. Let's apply the electron filling rules by placing 16 electrons into this diagram. The 1s orbital holds 2 electrons, one spin up and the other spin down. So it is completely filled. Next, we move to the 2s subshell, which holds 2 electrons of opposite spin. After filling the 2s, we move up to the 2p subshell. Every p subshell contains 3 orbitals of equal energy. This is where Hund's rule comes into play. Each p orbital gets 1 electron before pairing occurs. Once the 2p subshell is filled, we now have a total of 10 electrons. We need to add 2 electrons to the 3s subshell, leaving 4 electrons to place in the 3p subshell. Again, the 3p subshell has 3 orbitals. According to Hund's rule, we place 1 electron in each orbital before pairing. The result is 1 orbital with 2 electrons and 2 orbitals with 1 unpaired electron each. The 4s subshell contains no electrons in this case, so it did not need to be included in this diagram. The arrangement of electrons around an atom determines how that atom forms bonds and participates in chemical reactions. In particular, the electrons in the outermost shell are the most important. Because orbital box diagrams take a long time to draw, chemists often use electron configurations, which communicate the same information more quickly, but with less visual detail. In an electron configuration, we list the shell number and the subshell, followed by a superscript indicating how many electrons are in that subshell. Even though this is written like an exponent, we do not read it like one. For example, we read 1s2 as 1s2, not 1s squared. The same applies for 2s2, 2p6, and so on. Using our orbital box diagram, we can write the full electron configuration by listing each subshell and the number of electrons it contains. 1s2, 2s2, 2p6, 3s2, 3p4. This is called a full electron configuration because it includes every electron in the atom. Often we are most interested in the outer electrons, since they control bonding and reactivity. To focus on these, we can write a noble gas abbreviated electron configuration. In this method, we replace the inner electrons with the symbol of the closest noble gas that comes before the element. The noble gas represents all the electrons that the element already has. In this example, with 16 electrons, the closest noble gas is neon, which has 10 electrons. We write neon in square brackets, followed by the remaining electrons. Neon, 3s2, 3p4. Electron configurations can be read directly from the periodic table, which means you do not need to draw an orbital box diagram first. Each column of the periodic table represents one electron. The S block is 2 columns wide because S subshells hold 2 electrons. The P block is 6 columns wide because P subshells can hold 6 electrons. The same pattern continues. D subshells can hold 10 electrons, and the transition metals are 10 columns wide. F subshells hold 14 electrons, and the inner transition metals span 14 columns. Let's do an example for a silicon 2- ion. Silicon has an atomic number of 14, meaning a neutral silicon atom has 14 protons and 14 electrons. A 2- charge means it has 2 extra electrons for a total of 16 electrons. Since this ion has 16 electrons, we will focus our eyes on a neutral element with the same number of electrons, sulfur. Now we read the periodic table like a book, from left to right, top to bottom, stopping once you reach the 16th electron. The top row is read as 1s2. Then we come down to the second row and we read that as 2s2. Coming over to the P block, that is the 2p, and we cover all 6 columns for 2p6. Then we come around to the third row where we have 3s2. Continuing on to the rest of that third period, we have the 3p, but we are stopping 4 columns in, representing 3p4. This gives us a full electron configuration of 1s2, 2s2, 2p6, 3s2, 3p4. We can also get the noble gas abbreviated electron configuration by starting at the previous noble gas, neon, and then reading off what neon doesn't have. 3s2, 3p4. Now let's do another example for a lead 2+ ion. Lead has an atomic number of 82, so a neutral atom has 82 protons and 82 electrons. A 2+ charge means it has lost 2 electrons, leaving 80 electrons. The noble gas before lead is xenon. After xenon, electrons fill the 6s subshell. Then we drop down to the 4f, and then we come back up to the 5d. The noble gas abbreviated electron configuration for Pb with a 2+ charge is xenon, 6s2, 4f14, 5d10. Here are some practice problems. First, draw an orbital box diagram for F-. Remember that the minus charge means that it has 1 extra electron, giving F- the same electron configuration as neon. In our orbital box diagram for F minus, we will have 2 electrons in the 1s, 2 electrons in the 2s, and then the 2p will be filled with 6 electrons. Now, write the noble gas electron configuration of lithium. Let's start with helium, and then write what helium does not have, 2s1. We do have to write the 1 for this electron configuration. Finally, write the full electron configuration for magnesium with a 2 positive charge. Magnesium has 12 electrons when neutral, but magnesium 2 positive has 10 electrons, giving the electron configuration of 1s2, 2s2, 2p6. Remember, when it says full electron configuration, that means that you're starting with the 1s.